Okay, guys, in this lecture, we're going to review Gauss's law. So this is something, again, you guys learned in 183. What Gauss's law tells us is how the flux of the electric field is related to the amount of charge inside a closed surface. So we thought about flux in the last lecture, and flux is really useful and interesting to think about, but we want to use it to learn something about electric fields, okay? So I want you guys to think about a couple of different charge configurations. The first is a parallel plate capacitor. Okay, so we've got a negatively charged plate, and on the other side, we've got a positively charged plate. And I'm going to move that over a little bit. Okay, and between these two plates, we have a constant electric field. If you guys remember, the electric field points in the direction a positive charge would flow. So it's going to point from the positive plate to the negative plate. And at least in between the plates, away from the edges, that field should be fairly constant. Okay, so that's our electric field. Okay, I'm going to put a surface in there, a closed surface. And to make it easy to think about the flux, I'm going to pick a surface whose sides are either parallel or perpendicular to the electric field. Because as we talked about in the last lecture, it's easiest to think about those two situations because then you either have maximum flux or zero flux through your surface. Okay, so this is a little bit hard to draw on a piece of paper. So imagine I'm putting a box in here where the sides of the box are either parallel to this electric field or they are perpendicular. Okay, so we'll throw a box in there. It doesn't have to be perfect square. Okay, I can define area vectors that are perpendicular to every side of this box. So that's what I'm doing here. All right. There's one there. Okay, and now let's think about the flux of this electric field through the box. Okay, so if I think about these two sides, okay, kind of like the leading side and the wake side, right? The field is coming into this side and it's coming out of that side. Okay, the flux on these sides actually, let me be more clear. I can number these. Let's call this 1, 2, 3, and 4. Okay. And then there's 6 sides. So we'll call that one 5. And be complete 6. Okay. So the flux on A1 and A3, those fluxes are going to be equal and opposite, okay? They're not going to be zero, but they're going to be equal and opposite. And the reason for that is that the electric field is, right, in the opposite direction, but parallel to the area vector here, but it's in the same direction and parallel to the area vector here. So we got a negative flux, and here we're going to have a positive flux. Okay, so those two sides are going to cancel out because the flux is equal and opposite. Okay, the flux through all of the other sides is 0. Okay, in that case, it's because the area vector is perpendicular to the electric field on all the other sides. Okay, so the total flux through this rectangle is 0. Okay, the total flux is 0. The field is literally just passing through, okay? So I want to think in this case, even though we have field lines going through our box, the field is just passing through, and we have a constant flux because there are no sources of the electric field or sinks, which isn't really a thing, okay, in the box. Therefore, there's nothing that's creating new flux in the box, okay? And even though I made a box here, okay, to make this problem easier, this would be true, okay, for any shape. Any shape I put, any closed surface I put in between these two capacitor plates. Okay, and in fact, even if I drew something more complicated to think about, so now I'm going to draw over here, even if I drew, let's make it a positive charge here, and that positive charge had, right, it's got an outward electric field like this. I can depict it with some electric field lines, okay, even if I drew a sphere out here and thought about the flux through the sphere, that would also still be zero, okay? It's a little bit harder to argue easily mathematically here. I think you can easily understand why the flux through the sides is zero, because the geometry is a lot more favorable for thinking about it. But if you think about this here, there is as many field lines that are coming into the surface here on this side. They're all passing through and leaving on this side, okay? So we've got a region where there's a lot of field lines passing through here in a small area, are entering our sphere. And then we have this large area where maybe the field is a little bit weaker. It's more, these field lines are more spread out from one another, but the area is larger that they're passing through, okay? So again, we still have a situation where the field lines are just passing through. There's no new field lines or new field created within our sphere here. So the flux through this sphere is still zero, okay? All right, so let's think about a simple configuration where there is some field created within a closed surface. So again, I'm just going to think about the electric field around a positive charge. All right, so we've got a radial or spherically symmetric electric field, and I'm going to draw a surface, and it's going to be a sphere, and the sphere is going to be centered. I can actually do better than that. The sphere is going to be centered, okay, right on our charge. Okay, so I'm going to draw this the best I can, but I'll make a note over here that the sphere has the charge at its center. Okay, I'll show you later that actually doesn't matter for our calculation, but it makes it easier to think about it. Okay, so because that the sphere or the charge is right at the center of this sphere, that means that the electric field is actually parallel to the little area vectors of our sphere. So I can draw a little area thing and make a little area vector that looks like that everywhere along the surface, okay? And I also know that the electric field, the magnitude of it, is constant along the surface. Okay, so that really simplifies things. Okay, so let's go ahead and think about how we can then calculate the flux through this particular surface, okay? So let's remember our electric field for a charge is just 1 over 4 pi epsilon naught q the charge over r squared times r hat, okay? And I want to use spherical coordinates in order to define these little surface area bits, okay? So I need to pick the right dA, and I'm going to replace dA with r squared sine theta, okay, d theta, d phi. Okay, and this one actually isn't in the back of the book, but d tau is. And if you remember how I defined d tau, as a little chunk of volume in the sphere, it should make sense that just the area of the top of that little chunk of volume, which is the surface area, is going to, okay, and of course I need to include the direction here because it's still a vector. So this is going to be in the radial direction. So I'm going to include an r hat here, which is a unit vector in the radial direction. All right, so now I want to take an integral over the surface. In this case, it's a closed surface, so I'm going to use this special integral sign. This basically means, hey, everybody, it's not just any surface. This is a closed surface. And if I substitute in what I did into that integral, I get okay, so some of this stuff I just pulled out because it doesn't depend on r, like the q. Okay, this came from this guy came from here. Remember, I'm dotting the electric field with this area vector, and these two things are vectors. Both of them are in the r hat direction, so that gives me this bit right here. Since these two guys are in the same direction, the dot product of them is just going to be their magnitudes multiplied by each other, or just 1. Okay, so 1, this is essentially the magnitude, and this should make sense, hopefully, of both of these vectors, which is like taking 1 times 1. Okay, so that's where the vectors go away. Notice, right, we're getting a scalar flux out of this. Okay, so we've simplified this quite a bit. Now I just have to, I'm going to put one of these guys over here too. Do this integral. Okay, so I'm going to replace my integral sign with the actual limit. So I need to, it's a surface integral, so I need 2 sets of limits. Okay, and I'll separate it out like this so it's a little more clear. My limits of integration in the phi direction, if you remember, that's the one that goes around the circle like this. So that one goes from 2 pi to 0. And then the theta direction, that one goes up and down from the z-axis. So if I wanted to do the whole sphere, that's just going to go from pi to 0. Okay. And if I do this integral, hopefully it makes sense to you guys that I'm going to end up getting 4 pi from doing the integral, multiply it by the rest of this fun stuff. Okay. And these guys are going to cancel out. So I'm just going to get q over epsilon naught is equal to the flux of the electric field through that closed surface. Okay, sweet. So in this case, we get something that isn't 0, okay? In this case, we get something that is non-zero and is clearly related to the amount of charge within our surface. Okay, and it isn't 0 because there's positive flux coming out of that surface. Okay, the field isn't just passing through anymore. Now there's a source of field inside our closed surface. Okay, this integral would have turned out the same way even if I didn't put this particular charge right at the center. Even if I put it over here or over here, what that would have done to my integral was just make it harder. There would have been a stronger electric field over here. And so, but it would have been over a smaller area. Over here, where the electric field would have been weaker, it would have been over a larger area. And actually, those two things would have balanced out, and I still would have gotten the same answer, okay? I could also have changed the shape that I decided to integrate this surface over, okay? So I just arbitrarily chose a sphere. I could have chose a sphere with a different radius. Obviously, that didn't matter. I could have chose a box. I could have chose a cylinder. As long as it was surrounding this charge, I still would have gotten the same answer here, okay? Lastly, if I put more charges in there, okay, so if I put 2 charges in here, instead of 1 or 3 charges or 4 charges, it's still, okay, I still would have gotten a non-zero flux, but this particular term here, it would have been bigger. So if I would have put 2 times the charge in here, I would get 2 times the flux, okay? So you can think about that simply. I just told you it didn't matter where I put the flux, or where I put the charge. So if I just stacked it right in the middle, okay, the only thing that would have changed was a factor in front of this Q, and that would have given us a factor in front of the Q here, okay? So one way to think about this whole idea of flux through a closed surface is to think about something like light bulbs, okay? So if you really knew how to characterize the light coming from a light bulb, you could probably determine the total amount of power of light emitted inside a surface, okay, by not actually needing to know the number of light bulbs inside a surface, but you could just carefully measure the intensity of light passing through that surface. And from that, the amount of energy coming through the surface, you could determine the amount of energy being produced by light bulbs within the surface. Just to really pound this home, I'm going to switch over to a Mathematica notebook where I am actually doing this integral for harder configurations, just to prove to you that it works even when we can't simply do it by hand. Okay, so this is just a Mathematica notebook I made for computational physics a few years ago. And basically, I'm just going to do some harder integrals with it. So you can read through this if you want. But what I'm doing here is I'm just defining some properties of the charges I'm going to put inside the surface. So this is the charge of each particle. I'm going to put 4 particles inside the surface, and I'm just going to randomly place them. So every time I run this, they're going to change their position. Okay. Here I'm calculating the electric field components for each charge. I'm doing it in a way where I can define this equation, and then down here I'm actually substituting in values for the x, y, and z components of each of the charges. So these are all the electric field components in the x, y, z direction for each of the 4 particles. And this is very repetitive. I wouldn't normally code this way, but I tried to make it as easy as possible to understand. Okay, the last thing I'm doing here is superposition. So I'm just adding together the electric fields for each charge to find the total electric field. This is some graphics stuff that I'm doing. Okay, and the last little bit down here, this is all graphics. And then here, it's actually doing the integral. And Mathematica is smart enough that you can just say, hey, integrate this over a sphere. I haven't got it to work for any other shapes, okay? The last thing I'm doing is I'm multiplying what I get out of this by epsilon, so I'm just getting Q. But the point is, if I run this over and over again, okay, the charges are going to move around. And when they do move around, that means that the flux through the surface is changing because some particles are getting close to the surface, right? And they're moving around and getting further away. So the flux through the surface isn't constant everywhere, right? It isn't even necessarily in a nice direction. Okay, but we can still have Mathematica do this integral. And no matter what I do, okay, it takes a little while to do that integral. I'm kind of going too fast here. As they move, I still get what I expect, which is the total amount of charge within the surface. And now I've made it so the vectors don't plot very nicely. There's a nice one. Okay, and I told you that I can do this for any shape. So here I'm essentially doing the same thing, but now I'm summing the flux over a cube instead of over a sphere. But I still have 4 different charged particles in the sphere. They have the same charge, and I can run this again over and over again. The particles move around, but as long as they are inside, okay, my cube here, then I calculate, when I do this integral and I multiply by epsilon, I calculate the amount of charge within the rectangle. Okay, the only thing left to do now is just to write out what we've been getting at this whole time, which is Gauss's law. Okay, so Gauss's law allows us to do things like calculate the electric field or the amount of charge within a surface by just considering the flux of electric field at a closed surface. So it has to be closed. Notice Gauss's law, that integral is only for a closed to surface, okay? But if I do an integral of the electric field over a closed surface, I'm going to find that it's equal to the amount of charge within that closed surface over epsilon naught. Okay, so this Q here is the amount of charge. And again, we're going to usually use, when we're doing it by hand, simpler cases, just so it's possible to do the integral by hand. But this works for any closed surface, okay, any shape I want, as long as it's closed, which means I'm calculating the flux over all of the sides. Okay, and it even works, this is kind of cool, it even works for moving charges. Coulomb's law, we're in electrostatics right now, it actually doesn't work for moving charges, okay? But Gauss's law works whether the charges inside of it are moving or not. So it's even more fundamental in that way than good old Coulomb's law.